Welcome students. I'm Anthony Gariavo from the School of Hospitality, Travel and Tourism, Department of Travel and Tourism Management. I'd like to welcome you today to today's lesson under the unit called CHT1319, that is Radio Theory and Communication Practice. In today's lesson, we shall discuss about waves. And why waves? Simply because radios normally operate using the principles of waves. So we shall explore and find out and see further where the radio waves lie on. That is why it's good for us to start and understand the meaning of waves and the principality of the functionality of waves. So today's objectives, we shall look at number one, what is the meaning of waves. Then number two, their classification. Then number three, we shall focus on to the electromagnetic waves and their uses. So first things first, let's look at the meaning of waves. What is a wave? A wave is normally disturbance, or I can talk about oscillation or vibration that travel through space, and after this traveling occurs, we normally have transfer of energy. So one thing I like to say about waves, when waves are produced, we normally have motion, and the motion automatically normally transfers energy from the point where this disturbance starts up to the point where the particles are displaced to the end point. And when this happens, we normally have no displacement of particles of the medium in that kind of in the process. What are the properties of waves? What are the properties of waves? One, from the definition, waves normally transfer energy. One characteristic of wave. And then number two, we normally have a repetitive kind of movement or a vibration or an oscillation. And then number three, when this movement of energy takes place, normally the medium or the particles, we don't have movement of the medium or the medium or the particles that are involved during the transfer of energy. And then we normally have number four, waves normally show the following structure. So if you look at this point, this is the point where the disturbance starts. And when this disturbance starts, it will end from this point and then end at the last point. But in the process of disturbance, we normally have a diagrammatic representation of the disturbance in this particular kind of a form, where we have the highest point called the crests, and then we have the lowest point normally called the trough. And then we normally have the highest point of the wave, we normally call it the amplitude. And then normally, according to the features of waves, we normally have wavelength. And wavelength is normally a measure between two successive crests, or it can be between two successive troughs with respect to the waves. So waves normally show this feature. So from what we have seen from the diagram, we have seen the amplitude, and amplitude is normally the highest point of the wave. And then the wavelength, you have seen the distance between two successive crests or two successive troughs. And then we have the period. Normally, waves normally show a feature of period, and the period is normally the time taken for the medium to take a complete cycle. And then frequency is all about the number of waves passing a point at a certain kind of a time. So normally frequency is normally measured in form of hertz per second. And then we have speed and velocity. When waves normally move, normally the all waves normally show one common feature. And the common feature is the speed at which it travels. It normally travels very fast at a speed similar to light. And then we have the speed or the velocity of wave, where it's normally measured in meters per second. This is the time that is taken to, during the displacement of a wave from one point to the other. And then I mentioned the crest. The crest is the point, is normally the highest point of the wave, whereas the trough becomes the lowest or the maximum point of displacement of the wave. Basing on the types of waves, we have two types of waves, basing on the medium that causes their displacement. One, we have longitudinal waves, and then you have transverse waves. Now, what are longitudinal waves? Longitudinal waves, these are types of waves whereby the oscillations are normally parallel to the direction of the displacement or their propagation. Now, if you look at this is an example of that representation of the displacement, where it has features of expansion and then compressions. From this diagram, if you look at expansion, now this is the point where you find that we have the density between the waves becoming less dense, whereas at the compression you find more density during the displacement. Now, one aspect about longitudinal waves, we have seen that the oscillations they're normally parallel to the direction of propagation, and you find that when these waves are being displaced, you find that we normally have a tendency of vibration of back and forth. Talk about a back and forth movement of the displacement. So one thing I like us to explore further, which are the examples of longitudinal waves? We shall explore further. Examples include the mechanical waves, we have sound waves, we have P-type earthquake waves, and then you have compression waves, especially when we talk about a spring. Now let me come back to the parts of the longitudinal waves. I mentioned compression, I mentioned rarefactions, where if we talk about compression, this automatically is a point on the medium through which the longitudinal waves normally, when they're traveling, it has the maximum density. We find that the density at that point is normally maximum. Now, which points represent compression? Compression automatically are represented by point A. Now, this way we have compression, and then point C, and then if you look at point E, this automatically represents compression. And then, if I talk about rarefaction, now rarefaction automatically, this is normally a point on the wave, this longitudinal wave, where you find that the traveling shows minimum density, meaning that there is less squeezing during that point, moment of traveling. And from the diagram, it is clear that rarefactions are represented by B, and then D, and then F. These are points of minimum density. Now, how do we measure the wavelength of longitudinal waves? They are normally measured between two successive compressions and then two successive rarefactions. That is how the wavelength are normally measured in longitudinal waves. So it is good for us to note this in advance, that we have transverse wave and then you have longitudinal waves. So if I go to transverse waves, these are types of waves that are characterized by the disturbance or the oscillations that travel at right angle or perpendicular to the direction of travel of the waves. Now, this is a representation of that. So we saw in the longitudinal waves we have we normally have parallel kind of displacement of the particles, but here in this kind of a case we're seeing perpendicular type of displacement. You can see if this is a straight line, you find that the displacement automatically takes place automatically at 90 degrees to the point of to the direction of the how the waves normally travel, or the disturbance normally travel. And we have discussed about wavelength, that is the distance from one successive crest to the other, or I've said from one successive trough to the other, the lowest point, that is. So the examples of transverse waves. We have electromagnetic waves. Now that is going to be a point of focus. And then we have water waves. Those are waves that are found on a ripple tank, for example. And then we have S-wave, earthquake waves. We have stringed instrument, and then we have torsion wave, of which these are normally type of waves that are normally remain when the two electromagnetic fields interfere and cancel out each other. So those are the examples of transverse waves. Maybe before I come further to this, I'd like just to mention the difference between the two types of waves. One, you find that in terms of displacement, you find that a transverse waves automatically has pattern of crests and troughs, and they normally show an angle of 90 degrees to the talk about in the direction of displacement of the wave. And then number two, if you look at longitudinal waves, we don't see crests and troughs, but we see compression and rarefaction, and this automatically is brought about because of the parallel displacement of the particles in the wave as it's traveled from one point to the other. And then the wavelength. How do you measure wavelength in transverse waves? They are normally measured from one successive crest to the next, or one successive trough to the next. Whereas in longitudinal waves, we normally measure the distance from compression to the next compression, or rarefaction to the next rarefaction. Let's look at electromagnetic waves. That is now the point where we want to focus on, because we are discussing about radio theory, and these are the waves that are of importance to us. So I would like to look at electromagnetic waves, which are, and we've said that these belong to transverse waves, and we have seen that in transverse waves, the displacement of, or the oscillation normally take place at right angles to the direction of the travel, the direction to which the wave is traveling to. And then what produces electromagnetic waves? Automatically, these are normally caused by vibration or oscillations that normally come about due to the changes in electrical and magnetic field. And when they happen, automatically electromagnetic waves are produced. So one feature about electromagnetic waves, number one, they transfer energy just like other waves, from one point of disturbance to the next point where the disturbance ends. And then number two, you find that they don't require any medium of propagation, meaning that they travel through space, or I can talk about through transparent electric media, meaning they don't need medium to enhance their traveling from one point to the other. So I've said they normally travel through space. And one aspect about electromagnetic waves is that they normally travel at a speed of light, that is the speed of 300,000 meters per second, that is through the vacuum, meaning they travel very fast, just like the speed of light. The examples of electromagnetic waves, these include radio waves. These are the waves that we are concerned about, telling us more about how radios normally work, their functionality. And then we have infrared radiation, we have visible light, we have ultraviolet radiation, and then we have X-rays, and then we have gamma rays. Those are the examples of electromagnetic waves. So what we shall do is we want to find out how are these electromagnetic waves, how are they organized, or how are they arranged with respect to the wavelength on the electromagnetic spectrum. That is what we want to look at. And one aspect I like to say is that they're normally organized from you find that waves are organized with respect to wavelengths, where you find that those that have short wavelengths, they have high frequency and high energy, and those with the long wavelength, they have low frequency and low energy. So their organization is normally organized from long wavelengths. We have those that have long wavelengths as they shorten towards those that have very, very short wavelengths. And we have seen the shorter the wavelength, the higher the frequency and the higher the energy, and the more risky or dangerous they are to to humans or any other matter that they normally come into contact to. So I'd like us to look at the electromagnetic spectrum, the ones that are the examples of wave that were mentioned. And if you look at this, you find that they are normally organized from those that have longer wavelength, and then they go all the way as they move towards gamma rays. You find that the wavelength becomes shorter and shorter, meaning more frequency, and then we talk about high energy. So if you look at radio waves, this is now where we get the radio waves. The radio waves automatically, they have longer wavelengths. They normally have longer wavelengths, and they normally have low frequency, and they have low energy. So this way we have the radio waves, followed by the microwaves. Then what follows is infrared, the visible light, ultraviolet rays, X-rays, and then the most powerful of them all, we have the gamma rays. Gamma rays are the most powerful of these, and you find that as you go towards X-rays, gamma rays, and ultraviolet rays, we talk about ionization type of radiation that are very risky, and they can easily cause hazard to into the lives of the human beings or any other living being, because they can penetrate matter when you move towards that point. Now, I'd like us to explore the different types of waves in the electromagnetic spectrum. And one thing I'd like to mention is that each group has a range of frequency, and this frequency automatically normally determines, and it tells us more about the wavelength versus the frequencies. And one thing I like to say is that a good example is, if you look at this example, the visible light, it has its frequency, and this frequency is the one that makes it possible for the human eye to detect it. And then you find that we shall look at this further as we move on now to look at the visible light based on that kind of a chronology or order, where you find that even in the visible light, you find that we see different lights of different kind of, talk about pigments or pigmentation or coloration. And even in the visible light kind of a spectrum, you find that the red light has its own kind of frequency, and then violet will have a different frequency from the red light. We shall look at that when we now look at the different, we look at the various waves on the that are with respect to the electromagnetic spectrum. So the first one is radio waves. This is now the most important wave of our concern. And one thing I like about radio waves is that they normally have longer wavelength. You have seen from the diagram, they have very long wavelengths. And if I talk about the frequency, the frequency normally range from 30 hertz to 300 gigahertz. And if you just put this in the normal kind of in the normal understanding, talk about in the easy understanding, we can the wavelengths automatically at this point, I'll say that the wavelength is from 1 millimeter, and then it goes to 10,000 kilometers. That is in the 30 hertz, 30 hertz measurement, and then in 300 we talk about 1 meter. So they are very long kind of wavelengths. And then what normally produces, how are they produced? They're normally produced by oscillation in the electrical circuits. And one aspect about radio waves, they normally require conductor, and the conductor normally is in the form of aerial, the aerial, or they talk about the antenna in a radio. And then for the functionality of a radio, it normally requires radio waves, yes. But now the radio waves are the one that we have said that they're normally produced by oscillation in the electrical circuits, and then they normally are they normally require absorption by a conductor, and the conductor becomes the antenna. And the antennas, or talk about the aerial, we normally see them on the radio, and this automatically become very important. Now, for the functionality of the radio, we normally have transmitters, and then we normally have receivers, where the antenna plays a role. It normally plays a very, very important role as a transmitter as well as a receiver. So I can say this, that information in the is normally carried via the radio wave, that is before the transmission, and then after which relevant information is going to be decoded out of that, and then information becomes clear to the person receiving the information. Now, what are the uses of radio waves? If you look at most of the functions of the radio waves, they're made possible because if you look at the features of radio waves, they have longer wavelengths. Yes, this makes them less harmful to the humans as well as other living beings, and because of that, you find that it makes it possible for it to be ideal in the use in the following types of uses. Talk about communication in broadcasting, and then we have the police radar. And if you look at police radar, a good example of the where we have the police radar is the speed gun. The speed gun normally makes use of radio waves. It normally looks at the speed of the motorists in the highways. We have the Doppler radar, and the Doppler radar is normally important in the weather station. It is important in measuring the precipitation in lightning, so that at least the rate of precipitation is normally discovered, and it can tell us more about the hailstorm that are coming, that are approaching the Doppler, the Doppler radar. Then we have global positioning system. Today, even our phones normally have the GPS's type of devices, and this automatically normally make use of the radio waves. We have satellite tracking, and then we have television and radio communication. We have cellular phones. We have even the networks that we normally use today in our computers. Go to the keyless entry. I know today hotels normally make use of this for security. The keyless keys that we have in hotels also make use of radio waves. I've mentioned broadcasting. Even garage, the garage normally open, the doors normally open automatically with the aid of the radio waves. We have the dog collars, and then satellite radios. They make use of the radio waves. Now that is radio waves. Let's look at the microwaves. Let's look at the microwaves. I know when you mention microwaves, one thing that comes out is cooking. It's all about cooking, because in our houses we normally have these equipments. But let's look at microwaves and see what makes it possible for them to make this function of cooking possible. Fine. If you look at microwaves are also electromagnetic radiations, and you find that they normally have a frequency of 300 megahertz and wavelength of 1 meter, and it ranges to up to 300 gigahertz. That is a wavelength of 1 millimeter in terms of the wavelengths and the frequency. What are the uses of microwaves? One, cooking, and also satellite communication. And you find that at very high frequency, microwaves normally have a tendency whereby they can easily be absorbed by molecules in food, and automatically, because of that, it increases the rate of heat as cooking takes place. For that, automatically they become good types of waves to make cooking possible. Also, they can be used in satellite orbits. They're normally used in satellite, where automatically, because it is easy for them to pass through the atmosphere and through the stations, it makes it possible for them also to be used in the satellite, on the satellite aspects in communication. Then you have infrared. Infrared, these ones normally have a range of about 300 gigahertz up to 400 terahertz. that is having a wavelength between 1 millimeter to 700 nanometers. Now, one aspect about infrared radiation, these ones automatically can be absorbed by some chemical bonds. And one thing I like to say about the infrared are normally important also in the area of cooking food, and then in the area of electrical heaters and cooking food, they're normally important. It is simply because they are normally the internal, I've said the internal energy of the bonds increases as they're normally absorbed by the infrared. So meaning that they normally tend to increase the energy, make it possible for increase in heating. And then we have, we also have, today we normally talk about the infrared cameras. Infrared cameras are normally used to detect objects in the darkness, and it's because of one kind of a technique, that is thermal imaging, and this automatically makes it possible for people to see in the dark. Today, even in the military, normally the infrared cameras and infrared kind of gadgets are normally used to make impromptu night kind of ambushes, so that people that are being pursued, they cannot see, simply because of the ability of these cameras to be able to detect objects in the dark. It is simply because they can detect heat very fast. The infrared radiations are normally, they can detect heat, and they can automatically tell us what kind of an image is there based on the warmth that they normally detect in the dark kind of areas. They also use in remote controls that we normally use in our home, in our televisions, even radios. Also in the fiber optics normally makes use of infrared radiation, so automatically becomes very important. Also is also used in the area of astronomy, that is detecting objects that are normally found on the very far from the planets as well as the galaxies. Now we have the visible light. Now this is the light that we can see. According to the spectrum, it has a wavelength between 380 nanometers and 760 nanometers. That is a frequency of 400 to 790 terahertz, and it can be seen by the human eye, meaning that it's normally important for vision. And then other functions of visible lights become important in optic communication. So with respect to the visible light, now this is why I said we shall discuss further. Also the visible light also has its spectrum, where it has 7 types of color that have different types of wavelength, and each color has its own type of wavelength. And if you can see, we have 7. We normally have 7 types of color that are normally seen by the human eye. And you find that if you look at this, you find that it starts from violet. Violet has the shortest wavelength, meaning it has the shortest wavelength. And then if you go towards red, red has the longest type of wavelength. So meaning that from red to violet, the wavelength normally tends to decrease. So we have violet. Violet has the shortest wavelength. Indigo, it follows violet basing on the wavelength size. And then we have blue, green, we have yellow, orange, and then red. Red is the one that has the longest wavelength as compared to the others. Now let's look at ultraviolet radiation. Ultraviolet radiation. Ultraviolet radiation, it has a wavelength of about 40 nanometers to 10 nanometers. And then it has frequency of 8 times 10 raised to the power 14 to 3 times 10 raised to the power 16 cycles per second. That is the frequency. Which are the sources of ultraviolet radiation? Sources normally include, number 1, main source is the sunlight. And then number 2, we have mercury vapor lighting, the lighting that have mercury vapor in them. They produce ultraviolet radiation. You have halogen fluorescent and incandescent lights, and then some lasers also normally produce ultraviolet radiation. So we normally have three types of ultraviolet radiation. We have ultraviolet A, ultraviolet B, and then ultraviolet C. Now, if you look at this one called ultraviolet A it has the longest wavelength, meaning it is less harmful. So you can, there's something that you're noting from this. The longer the wavelength, the less harmful it is to the humans. So this one is called ultraviolet A, also called black light. And if you look at this, it has the longest wavelength, meaning it's less harmful to the human life. And you find that this type of ultraviolet A becomes important, especially in normal life, where at least insects and birds can perceive. And then those people that have cases of aphakia, that is a kind of a defect, talk about in the eye, because of missing optic lens, they can also see this. So we have ultraviolet B. This one is the one that is responsible. It has a range of 290 to 320 nanometers. This one causes sunburns, is the one that is responsible for the sunburns that we normally experience on the skin. And I'll say that too much exposure to this automatically is one that can lead to cancer. So this is the one that normally causes skin cancer if too much exposure is made possible in the atmosphere. So one aspect I'd like to say, if you look at ultraviolet B, when it comes from the sun toward the atmosphere, we normally have absorption taking place onto this ultraviolet B type of light, and 95% is normally absorbed with respect to the Stanford Solar Center, based on the reference for that. And then ultraviolet C, this one has a range of 100 to 290 nanometers. This one is now very dangerous as compared to the others, and it is easily absorbed into the Earth's atmosphere. And it is the one that becomes important, especially in the area of disinfecting food, air, in order to kill microorganisms. That is by destroying the cells, nucleic acids of these germs that are normally found in the food. So what are the uses of ultraviolet radiation? I think from this it is clear that ultraviolet radiation becomes important to disinfect food, to disinfect water, and possibly to disinfect air. Where we have germs, they normally destroy. Ultraviolet C does that function. And then we have talk about production of vitamin D, which becomes important. But I know too much exposure of vitamin D causes skin cancer. Now let's look at the last types of electromagnetic waves, that is X-rays and gamma rays. Now this introduces us to yet a very powerful type of radiation. We call it ionization radiation types of waves. And why do we say ionization? It is simply because when they come into contact with the electrons, you find that the shells of the atoms, when they normally come into contact with the electrons, you find that they normally cause an effect on them, turning them into ions. They normally turn them into ions. So they normally knock on the electrons and then turning them into ions. And when this happens, what normally happens? They normally cause mutation of cells. They cause cell mutation, and this automatically leads to cancer. That is why exposure to these two types of rays becomes very, very hazardous when one is exposed to them, because of this aspect of ionization energy. So X-rays. X-rays, we have seen from the electromagnetic spectrum, are shift from the radio waves up to the gamma rays. You find that the more we shift towards the gamma rays and the X-rays, the wavelengths become shorter, and then the frequencies also become higher, and the energy also increases in the process. So X-rays, these ones normally have high frequency, and they normally have wavelengths from 0.01 to 10 nanometers, and then frequency of 3 times 10 raised to the power of 19 to 3 times 10 raised to the power of 16 hertz, meaning they travel very, very fast in terms of frequency. And one thing I like to say, how are they produced? How are the X-rays produced? They're normally produced by the production, they normally originate outside the nucleus, and they're normally emitted by electrons. One aspect about X-rays. And one thing I like to say is that who discovered this? Who discovered this? There was a German scientist called Roentgen. He discovered this one in 1895, and he discovered this through an experiment. And up to date, you find that today we normally have the X-ray tube, which automatically produces the X-ray type of radiation. And why did he call them X-rays? It's simply because he called them X, simply because they are unknown radiation. And that is why up to date, there is people stuck onto them as X-rays, simply because according to the discoverer, he discovered unknown radiation which he could not understand, and he was doing further research about them, and of which today, up to date, they are referred to as X-rays. So they're normally produced through an X-ray tube, and one thing I like to say about X-rays and X-rays, we normally have two categories. We have soft X-rays and hard X-rays, where they normally vary based on the wavelength. And you have seen, if you look at soft X-rays, soft X-rays have relatively short wavelength of about 10 nanometers, and X-rays have wavelength of about 10 picometers. So one aspect about these types of waves, why soft, why hard, is simply because hard X-rays are normally seen as harmful, and in fact they normally occupy almost the same electromagnetic spectrum region in the gamma rays, meaning what? Hard X-rays are more penetrative and more dangerous as compared to the soft X-rays. So what are the uses of X-ray? We know in hospitals they're normally important to study the bone structure, and the ones normally used are the hard X-rays because they can penetrate matter. The soft X-rays are not normally used simply because they normally tend to be absorbed by matter, and that is why in hospitals they normally prefer hard X-rays. So we have X-ray. The X-rays are normally used in X-ray astronomy, where I know astronomy is all about studying celestial bodies. They become important in the gadgets that are normally used in astronomy. And then number two, X-ray. We have X-ray microscopy, and X-ray microscopy. Now this is now where we have production of production of images of very small objects through the use of electromagnetic radiation. So we have X-ray microscopy, and then you have X-ray fluorescence. And in X-ray fluorescence, this is normally used in the field of medicine. Now this is where a liquid is normally ingested by the patient, and then you find that X-rays are normally used to follow up how the liquid is moving, so that if there's any defect in the system of a person, automatically the defect automatically can be detected in the process of the movement of the item ingested by the patient. And then you have industrial radiography. Now this is now where the X-rays are normally used to detect if there are any cracks in the welded materials that are normally made in industries. So they're used to detect if there are any cracks in any kind of a welding material. It can be pipes, for example, so that if there's any kind of a pipe that is causing a leakage, automatically X-rays can be used to detect the crack so that it can be sealed or it can be replaced. And then we have we also have talk about in the area of art, where X-rays, we have X-ray spectrum microscopy, where this automatically tells us, it aids to especially the people who are in the art industry to determine if the pigment that has been used in that kind of a painting, automatically if it is okay or it's not. So this is used to detect that. In airport security, even in our institutions today, because of security, we also have the use of X-ray in terms of the scanners. These scanners automatically detect what kind of objects are normally in the bags. If there's any kind of a dangerous weapon that is not acceptable to be carried, automatically X-rays become important to detect that. So we also have the movement of bones. So I think this one I've mentioned. Talk about, we have Roentgen stereo photogrammetry. This automatically used to track movement of bones based on the implantation of the makers. And then it also used in X-ray photoelectron spectroscopy. Now this automatically is important, especially looking at the aspect in surface science, looking at this automatically normally relies on photoelectric effect so that it can look at the surface that is being that is of interest in that kind of a field. And then you have border control. In border control, you have scanners that are normally used to inspect tracks in the border, so that this automatically can tell if this kind of a track is carrying any kind of a material that is not wanted. And then we have also authentication and quality control of packaged items. Still, this border control and this other one of authentication is also important in looking at the goods that are normally in the trucks. And then you also have industrial computed tomography. Now this is now where X-rays equipment normally used to produce three-dimensional presentation of components, both externally and internally. So it also becomes important in that area. Now the last, let's look at the gamma rays. Gamma rays are the ones that have the shortest of all the wavelength, meaning they have higher frequency, meaning the more a wave has lesser talk about shorter wavelength, the frequency tends to be greater, more faster, meaning because of the movement of the wave becoming faster. Now we have the gamma rays. Gamma rays, these ones automatically have wavelengths of less than 100 picometers, or I can talk about 4 times 10 raised to the power of 9 inches, meaning that is a shorter kind of wavelength. It has frequency of 10 raised to power of 19 cycles per second, or hertz. Now, how are they created? They're normally created by nuclear decay and are emitted by atomic nucleus. That is how we can differentiate them from the X-rays. And then gamma rays and hard X-rays, I've said they normally overlap, and sometimes it's normally hard to differentiate them. Meaning what? I mentioned earlier on that hard X-rays are the ones that have high penetrative power, and they're very harmful as compared to the soft X-rays. So that's why if you look at gamma rays, they have the same kind of a feature. Sometimes it may be hard to differentiate them because of the penetrative kind of ability. Now, one aspect about gamma rays, what are the uses? They're normally used to treat cancerous tumors, where they normally destroy the nucleic acids of the tumor cells. They're also used they're normally used especially in search of minerals, because they normally emit their emissions are normally they aid to detect elements. So in airborne surveys, these gamma rays are normally important, and they're normally used to search for minerals because they contain radioactive elements, which are these uranium and thorium, and through the emissions automatically one is able to detect what kind of minerals are found below the Earth's surface. So they become important in the area of mining. And then also in the area of aerial and ground-based gamma ray spectroscopy. It also becomes important, especially in the area of geological mapping, mineral exploration, as I mentioned. Here, in the area of airborne surveys, it tells us more about where are the minerals because of the emission of the radioactive elements, uranium and thorium. So that is the end of our lesson today. Thank you very much.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.